So, welcome back to the second part of Chapter 8, where we continue our lecture on solutions and aqueous reactions and a whole bunch of other fun stuff. So now that we know about how solubility works, there's still some more pieces of information that we need to understand about solubility of different compounds. For example, ionic compounds. When an ionic compound dissolves in water, as I've demonstrated in the previous lecture, the resulting solution is going to contain not the intact ionic compound itself, but the ions of that compound. So if we dropped salt into water, we don't have little salt nuggets floating around. What happens is the sodium and the chloride get pried apart and completely surrounded by water molecules. And in that, we would say that water dissolves salt. Now, not all ionic compounds dissolve in water, which is to say not all ionic compounds stay in their ionic states when they're in water. And when we were in lab, for the short time that we were in lab this term, you guys actually did a lot of experiments where you created precipitates, where you took two compounds that were by themselves soluble in water, that was dissolved in water, and when you mixed them together, you created something that wasn't dissolved in water, something that fell out of being dissolved. So what we see here in this picture is silver chloride. Silver chloride is one of those classic solutions that are precipitates that get made because we can easily use silver nitrate, which stays dissolved in water, but the minute you expose silver nitrate to another compound or another solution that has chloride in it, then silver and chloride will come together and create a precipitate, which will end up in the bottom of your beaker or your test tube in the form of some sort of a cloudy, white, murky substance. So when a compound stays completely dissolved in water, and your solution looks like just pure water, we would say that you have a compound that is soluble in water. And when you have a compound that falls out of solution or doesn't dissolve at all, we would say that is an insoluble compound. So to kind of reiterate what was just stated, if you had a solution of silver nitrate, you would have ions of silver and ions of nitrate floating around in that solution, and your solution would actually look clear, like it was nothing. And you've seen this solution in lab many times. You worked with it a lot when we did all those precipitate reactions and created the charts. However, once you add something that has chlorine to your silver nitrate, something that has the chloride ion, you're going to create silver chloride. And silver chloride is almost completely insoluble, and it will fall out of solution and end up as some sort of a white substance in the bottom of your beaker. And that's what we see happening here on this slide. So how do you know when a salt or a compound is going to dissolve in water? Well, there is no simple way to look at the periodic chart and make a determination of that. There are factors that come into play, but the charts that we've used in class, the charts that you see in the book, all the guidelines that you see, were basically compiled by people who did repeated experimentations where they mixed certain compounds and they found that precipitates formed almost all the time or didn't form at all. And so determining whether a compound is going to be soluble in water or not is really a matter of using a chart. This slide says the best way to do it is by experiments, but I find that it's just as reliable to use a chart. Every once in a while you get an odd variant, and we've experienced that in lab too, where there could be something wrong with my chemicals or there may be some contaminant left in a test tube. It's always a good idea to go ahead and test everything, but you can make some pretty good predictions based upon an existing solubility chart. So your textbook gives you some solubility rules that are going to act as guidelines about what will dissolve in water and what won't. And I personally find this a little convoluted. So if you start in the square at the top left, it says these compounds are generally soluble, and it lists them all out. And then you have all these exceptions, such as with silver and mercury and lead, or sulfate and strontium and barium, all these different things. So trying to read it off the paper like this, I find is a little bit difficult for me to process mentally. So I have some other charts that you might find more useful. So this is a Solubility Rules flowchart. There's actually two of these, and they deal with different sorts of compounds. So if we look in the far left here, let's say that you had a compound of lithium oxide, and you would find in this chart your lithium right here. So if you have a compound that contains lithium, and lithium oxide would contain lithium, then you follow the arrow, go down here, and it's going to tell you, oh, well, then your compound is going to be soluble in water. Let's say that you had another compound. Let's say that you had something like sodium chloride. Well, you could look up the chloride right here and follow the little arrow because our solution does contain chloride. And then, oh, we got another box. And this box says, does the compound also contain silver or mercury or lead? Well, it doesn't. In our example, it's going to contain sodium and chlorine. So the answer is no. We would follow the arrow off to the left, and that would be soluble. That means it's going to dissolve when it's in water. So let's say that we were dealing instead with, instead of sodium, we were dealing with silver chloride. Well, we've got a compound with chlorine, so we're going to go to the next box, and oops, yep, we've got silver right there. So we would have to answer yes, and then we would find out that we're dealing with something that's insoluble. So, and it follows the same way with the sulfate ion. And if your compound contains sulfate, you have to ask yourself, does it also contain any one of these? Calcium, strontium, barium, lead 2 specifically. And if the answer is yes, then you're dealing with something that is insoluble. If the answer is no, then your compound will be dissolved in water. We have some other ions of interest, such as the hydroxide ion. And the same thing, if you have a compound that has hydroxide in it, you can ask yourself if it has one of these. The answer is yes, then you would have a soluble compound. If the answer is no, it does not contain any of those. Let's say your compound contains calcium hydroxide. You come to this next box and you go, oh yeah, I've got calcium right here. Does my compound also contain calcium? Why, yes, it does. Then it would tell you that what you're dealing with is something that is only slightly soluble. So this is how these flowcharts work. You have to ask yourself, what is a compound that I can look at on this chart? And then what is the next box? And then you would answer yes or no to that, and then see whether you've got something that's insoluble or soluble, or maybe even just slightly soluble. So some exciting things happen when we mix two aqueous solutions. So let's say that we have a solution of sodium chloride and a solution of potassium fluoride, and we wanted to mix them together. What would happen in the vat with everything in it? Well, it would certainly contain all the species that we had from our start. So we would have sodium ions and chloride ions, and we would also have in this new solution potassium ions and fluoride ions. So we might be asking ourselves, what could happen once we mix everything? Well, what can happen is that you have a little do-si-do, a little partner swapping happen, and it's possible then that what you create once you mix these solutions are some new compounds. How are we going to express this to our reader? How can we do that? Can we put this in a chemical equation and let our readers know that some sort of magic has happened in the combining of our two aqueous solutions? Why, yes, we can do that. We can say, yeah, we started off with sodium chloride and potassium fluoride, and we ended up creating maybe some sodium fluoride and some potassium chloride. And what we know about the solutions off to the left of the transformation arrow was indeed that they were aqueous. That was that our salt was existing in its ionic form. On the right side of the transformation arrow, we cannot easily make the determination about how our new compounds are existing. In order to do that, we would have to consult a solubility chart of some sort to figure out whether these were aqueous or whether we formed a precipitate. And in that way, we could convey this information to our reader. So precipitation reactions are reactions in which a solid forms when two solutions are mixed. The insoluble product is then called a precipitate, and it gets noted in a chemical equation with an S. S stands for solid. So if we brought back our reaction of sodium chloride, and this time we reacted it with silver nitrate, we know that we're going to likely create something new. So let's start off with all four of our species of ions. So our possibilities are that instead of coupling up as sodium chloride and silver nitrate, we could actually end up with silver chloride and sodium nitrate. And if we consulted a solubility chart, we could say that, yeah, we started off with aqueous sodium chloride and aqueous silver nitrate. We would have to see what we had left as far as who was aqueous and who wasn't. After consulting a solubility chart, we would find that sodium nitrate is indeed aqueous and that silver chloride is the precipitate hanging out in the bottom of our vat. Here's a nice example about mixing lead to iodide. So you start off with a clear solution, a couple of clear solutions, and once they're mixed, you see that amazing yellow cloud form. This is a precipitate, and you would express it as PbI2, lead iodide, and you would put that in, you put that S in parentheses after this chemical formula to let your reader know that, yeah, we formed a precipitate. So what happens when there's no chemical reaction that has occurred? Well, let's take sodium chloride and potassium iodide and we mix them together. And after consulting a solubility chart, we see that we end up with no reaction, that our sodium iodide also stays aqueous and our potassium chloride is aqueous. So even though we would write them as having switched partners in our chemical reactions, we could write that. The fact that they stayed suspended in solution as ions means that they didn't do anything. All four of them existed as ions on the left of the transformation arrow, and they remained ions on the right of the transformation arrow. So in these sorts of scenarios, you would communicate to your reader that no reaction occurred by actually writing as a product, no reaction. If you did write it out and you said that you had sodium iodide aqueous and potassium chloride aqueous, you're really kind of wasting your time because they were aqueous on the left, they're aqueous on the right, nothing happened. So it's just faster to write NR for no reaction or write out no reaction. So what are the steps as far as predicting precipitation reactions? How do you go about writing these chemical equations? Well, you determine what ions are in each of the aqueous solutions, and you determine the formula of the possible products, which means that your ions are switching partners, are doing that do-si-do on the product side of the transformation arrow. And you want to balance everything out. That's the right way to do that. And then you would consult a solubility chart, and you would determine the solubility of each of the products that was created. And if you found that neither product created a precipitate, you would simply write no reaction or an NR after your transformation arrow. If one of your products is insoluble, then you would write the formula as of the products, and the one that formed the precipitate would receive that S in parentheses standing for solid, because now you have something that is in a solid form in your vat. And any other products you would write with the aqueous designation, the AQ in parentheses. And then at the end of that, you would want to balance the equation. And remember, when you're balancing your equations, the only numbers that you change are going to be the coefficients in front of your formulas and not anything that's in the subscript, because now you're changing the recipe and you don't want to do that. So let's say that we have this equation where we've mixed our sodium chloride aqueous and our silver nitrate aqueous, and we realize that we created sodium nitrate aqueous and a precipitate of silver chloride. When we write it as you see it on the screen, we have listed out every possible molecule. Even though the product that was aqueous, we've listed it out. And in this, we would say that we have written out the molecular formula for our aqueous reaction and the precipitates that were created. Now, what's actually happening in here can be further analyzed by writing this type of equation in what's known as its ionic form, the complete ionic equation. So what we would do then is we would take each one of these ionic formulas and we would write them in their ionic state. So for example, sodium chloride, instead of writing it as a formula, we would say the sodium ion aqueous and the chloride ion aqueous. And for sodium nitrate, we would do the same thing. We would say silver ion aqueous and nitrate ion aqueous. And when we wrote out our formulas, our products, look very carefully here what we did. We said that we still had sodium aqueous and nitrate aqueous, but now we have silver chloride solid. So this second writing of the formula, where we give all the ionic designations, is called a complete ionic equation. We've included everything that was in the molecular equation, except we put it in its ionic form. So when you're writing the ionic equations, things that receive that aqueous designation are things that are going to be dissolved in water as their ions, and things that are insoluble, and you could even include weak electrolytes in this, but certainly things that are insoluble or non-electrolytes would be written in the molecular form. So our precipitate, which is a solid, gets that S designation. If in the process of combining our formulas, our compounds, we created water, water would receive the designation of a liquid because it's not an electrolyte. It's a molecule, so we would have to say that it would be a liquid. And of course, if we created a gas somewhere, like something that bubbled, then we would have to write that gas with a G following it. So those are some things to keep in mind when you're writing out these equations. For the most part, for what we're doing here, we're really going to be isolating our equations and looking at whether we're creating a precipitate or not. So we're going to be pretty much sticking with a metal, non-metal sort of formula. But later on, when we start looking at different types of reactions in this chapter, you will see these designations, and I want you to have an understanding of what the parentheses around an L is and why it's there, or the parentheses around the G, what that is and why it's there. Now, in writing the complete ionic equation, you might have noticed that some of the ions on the left side of the transformation arrow stayed ions on the right side of the transformation arrow. So if we look at what's happening in our vat, you see that we have sodium and nitrate and silver and chloride all entering into the products portion of our vat, and that we have the possibility of our partners doing the do-si-do. And when we do, we actually create that silver chloride down at the bottom of the vat, that cloudy substance. But look at what happens with sodium and nitrate. They stay ions. So if we come back to our equation, we can see that sodium is an ion on the left side of the transformation arrow, and it's an ion on the right side of the transformation arrow. In fact, it didn't do anything, and it's a repeating term. We could actually kind of maybe cross that out. And if we look at nitrate, we can see that nitrate is an aqueous ion on the left side of the transformation arrow, and it is also aqueous on the right side of the transformation arrow. So we could actually cross that repeating term out. When we do that, what we see then is that what we have left behind is the chlorine ion, the silver ion, and our new product, silver chloride. So the only things that underwent any sort of transformation were the chloride and the silver. So what about the sodium and the nitrate? What would we classify those as? Because they didn't do anything. All they did was hang around in the vat and watch silver and chloride do something. Well, there is a name for those, and we would call them spectator ions. So the silver and the nitrate would be considered spectator. because all they do is watch. They're creepy, voyeuristic ions. They watch. So if we have some stuff hanging out in our vat that's not doing nothing, could we rewrite this equation yet one more time and eliminate all those do-nothing spectator ions? Why, yes, we can. And when we do, we would be writing the net ionic equation. So that's a much, much simpler form. And in this case, all we would take is the chlorine, the silver, and the new compound that was formed, which was silver chloride, and write that in its own equation. That is your net ionic equation. You can't get there from here without going through the other steps. Not easily, and probably not with any great accuracy. You kind of need to start off with your molecular formulas, or at least your formulas, and then do your net ionic equation, figure out where your spectator ions are, and then you can come up with this. So just to review what we just covered, we have a molecular equation which includes everybody written as a formula. So if I dump sodium chloride in a solution and silver nitrate in a solution, I did the partner switch in the do-si-do, I could end up with sodium nitrate, aqueous, and silver chloride as a solid. If I took all of these and I teased them out into, oh yeah, there's our spectator ion right there, creepy voyeuristic spectator ion. If we were to take all of these and put them in their ionic forms, it would look like this. We would have a complete ionic equation. And if we got rid of our spectator ions on both sides of the equation, we would then end up with our net ionic equation. So these are the three ways to express what's happening in your vat. All right, let's talk a little bit about acids. So acids are molecular compounds that when put into water, they form hydrogen ions. So when you write about an acid, you're always going to want to designate that it's aqueous. If you don't designate it as aqueous, that means that it's sitting in a jar somewhere in a chem lab as basically something that looks like a salt. So, and when it's a salt like that, it's basically going to be bound to its anion. The hydrogen is going to be bound to its anion. So technically it's not really an acid in that form. So it has to be dissolved in water for it to be considered an acid. It has to be to actively release that hydrogen ion. Now acids are going to be composed of hydrogen. And when we write them, we're going to write the hydrogen in the first position of the formula. Now, the next thing that we write is going to be the non-metal. That'll be written in the second position. And anything else that we would have, like an oxygen, that would be written in the third position. So typically the format that writing an acid is going to take is that you would have a hydrogen, and then you would have a non-metal, and then if you had something else, you would probably have an oxygen, and then that would be in the third position. Properties of acids. They're sour. Think about your lemons. Think about eating too many tomatoes. I don't know about you, but when I've grown tomatoes in a garden, boy, sometimes it's so good to stand there and eat them. You might eat two. Can get a little sour, tasting, burn your mouth. Oh yeah, that's always a lot of fun. Another property of acid is that it can dissolve many metals, and it can certainly create skin irritation, like when you eat too many tomatoes standing in your garden. Guilty. I used to do that, but it was so good. The more we've come to learn about acids, the more complex our definitions about what an acid, and a base for that matter, became. But the simplest of the definitions was first given to us by our good buddy Svante Arrhenius. And his observation was that an acid can be classified as a substance that is releasing hydrogen ions in water. So it's producing hydrogen ions in water. So we see our hydrochloric acid here is going to undergo a reaction where in water it's going to make those hydrogen ions and some chloride ions. Now, your book goes into a little bit about polyproduct ions. Poly means many. The prot means proton. And ic means pertaining to. So a polyproduct ion is a polyproduct acid is one where you have more than one hydrogen that can be liberated once your compound is dropped into water. Sulfuric acid is an example of this. We have two hydrogens hanging out there in the front of our formula, and both of those will get released. They get released in succession. So the first one comes off and then the second one. Because it has those two hydrogens, it's called diproduct, a diproduct or diprotic acid. Di meaning two, so it has two that it can get rid of. If you had three hydrogens hanging out in the front of your formula, it would be a triproduct acid. So that's a little bit about acids. Acids liberate hydrogens when released into water. Bases, on the other hand, are substances that produce hydroxide ions in water. Sodium hydroxide, the classic example, when you put sodium hydroxide in water, it's going to liberate into the sodium ions and the hydroxide ions. So here's some common acids and bases. You can find this table in your book. It's table 8.2. So if we look to the left, we see the hydrochloric acid. And if we just look at the formulas, you see that there's an H in the first position of all of those. And what follows is going to be a nonmetal or maybe a nonmetal and an oxygen. If you look to the right, you would see some common bases. And you will see that for the first 1, 2, 3, 4, 5 of them, they all have a hydroxide in them. You get down to ammonia, and ammonia does something a little bit different. The ammonia, NH3, is a base. And even though it doesn't have a hydroxide attached to it, its ability to snatch, remember this is in water, and its ability to take a hydrogen from a water molecule is pretty strong. And in fact, it does. And in the process, it leaves behind a hydroxide. So the action of ammonia is one of the reasons why we had to expand the definition of acids and bases, because Arrhenius's definition didn't include the actions of ammonia, being able to strip away a hydrogen from a water molecule and leave that hydroxide in its wake. So you've already seen this, but I'm going to point out the details. So we have binary acids and we have oxyacids. So binary, what does binary mean? Binary means you got two of something. Well, a binary acid is going to be an acid that's composed of a hydrogen cation and a nonmetal anion. And so it's a pretty basic formula. It's just going to be two compounds put together acting as an acid. Examples of this are hydrochloric acid, HCl, or hydrofluoric acid, which is hydrogen and fluorine. Now your other option here is the oxyacid. What do you think that means? Well, it probably means an acid with some oxygen in it. So these are going to be compounds that have the hydrogen cation, a polyatomic anion that's going to include a nonmetal and an oxygen. So there's your formula for your oxyacids right there. Some examples of this are nitric acid and sulfuric acid. So you can see the way that these are written follows this format with the H in the first position, your nonmetal in the second, and the oxygen in the third position of your formula. Yes, we have an abundance of flowcharts in this lecture. So when you classify an acid, first of all, you can pretty much guess that you're dealing with an acid because it's going to have that H in the first position of the formula. But then you have to take a look beyond that and say, are there just two elements? Are there two elements and an oxygen? Am I dealing with binary or am I dealing with an oxyacid? You can think of it this way. Binaries are going to have hydrogen and a nonmetal, oxyacids, hydrogen, nonmetal, and an oxygen. Oh, how do we name things? You know how the chemists are. They love to create rules. You know, that's what those IUPAC parties are all about. Ways to torture chem students with elaborate naming schemes. Well, fortunately, naming acids really isn't that hard. Binary acids are pretty simple. The first step is to write the hydro prefix. Got to give nod to that hydrogen sitting at the beginning there. And then the next thing you do is you're going to write the nonmetal name, except you're going to change it just a little bit. You're going to give it an ic ending. And then the last thing you do is you write the word acid to let the world know, yeah, I know I got an acid. I know it. So let's take a look. How would you write a compound made up of hydrogen and iodine in aqueous solution? Well, if we follow our rules, the first part of the name is going to be hydro, and that I stands for iodine, so we write iodine, but we got to change it. We got to give it that ic ending, so we're going to get rid of the ine and make it ic. And the last thing, acid. So putting it all together, hydroiodic acid. There you go. That's how you name a binary. So we've played with renaming nonmetals before when we were naming our compounds, like sodium chloride, when we gave the "ide" ending. So instead of an "ide" ending for the nonmetals, we're going to give it the "ic" ending. So let's try our hand at some more. So what if we had hydrogen and chlorine together in an aqueous solution? What would that be? Well, if we follow our formula, we would start off with hydro, and then we got to do something with that chlorine. We're not going to call it chloride. No, no, no. We're going to call it chloric, and we got to give it its last name, which is acid, so hydrochloric acid. What about hydrogen and bromine? Hydrobromic acid. What about this guy? Do you think those two hydrogens make any difference? No. We just say hydro. Even though we got two, we're just going to say one hydro. And what about our sulfur? S stands for sulfur. We're going to call it sulfic acid? Well, if you put that on an exam, I'd give you credit for it, because I suspect you're probably not a member of the International Union of Applied and Pure Chemists, or whatever they are, pure and applied chemists. But we would say sulfuric acid. So it would be hydrosulfuric acid would be the name of that. So again, just follows that pattern, which is thankfully very easily done. Naming oxyacids is a little bit more complicated, and there's a reason for that, and we're going to take a look at it. So let's get started. So oxyacids are going to be acids that contain oxyanions, and all an oxyanion is a polyatomic ion that contains oxygen. And you're going to find it on a polyatomic ion chart. Your book has them. You can find them online. So don't panic. You've already seen oxyanions. I just didn't call it that. So these acids, these oxyacids, are going to be a combination of one or more hydrogen ions with that oxyanion. And of course, the number of hydrogen ions is going to depend upon the charge of the oxyanion, because our formula has to be neutral. So if we have an oxyanion that has a -2 charge, then that means that we're going to have two hydrogens with each one having its +1 charge to offset the -2 charge of our oxyanion. So, for example, here we have hydrogen and nitrate. HNO3 contains the nitrate ion, so we're going to have just one hydrogen there. Nitrate has a -1, so we're just going to have one hydrogen in this formula. Here we have H2SO4, and this contains the sulfate ion. Sulfate is an oxyion. It comes in with a -2 charge, which is why we're going to have two hydrogens in this formula. Here we have another SO combination. This is called a sulfate ion. This one has 4 oxygens. The sulfite only had 3 oxygens. But the sulfate also has a -2 charge, which means we need to have 2 hydrogens to offset that -2 charge and give us a neutral formula. So here's a funny thing about oxyanions. They can have more than one in a series. In fact, they do typically come in series of at least 2, sometimes up to 4. So what do I mean? Well, if we look at nitrate and nitrite, you see that nitrite is NO2 and nitrate is NO3. So it's a difference of 1 oxygen. And those oxygens make a difference in the ion's strength, its ability to liberate that hydrogen. And they have different names. And the "ite" ending means that you have the one in the series that has less oxygens, and the "ate" means that you have the one in the series that has more oxygens. It doesn't tell us how many oxygens, it's just more or less than. We don't really need to know at this point. We're still using charts. Chart usage is absolutely acceptable in this class. So how would we name an oxyacid made with a nitrate versus a nitrite? Well, oxyacids ending with an ITE in their oxyanion state, the acid would get an OUS ending. So what do I mean? I mean that if we used nitrite in an acid that is HNO2, the name of our acid would be nitrous acid. So we go from nitrite to nitrous. Oxyanions that have the ATE ending are going to form acids with an IC ending. So if we took HNO3, which uses the nitrate oxyanion, our acid becomes nitric acid. So here's a nice chart that shows some of the common oxyacids and their anions. So we can see here we have HNO2 and HNO3. It is a nitrite and a nitrate, and here's our endings, us and ic. Here we have a sulfite and sulfate. We have chlorite and chlorate. And then we just have a couple of 8s right down here. But you can see the naming when it comes to naming the acids using each one of these oxyanions, depending upon which version of the oxyanion you're using in your acid. So let's try our hands at naming some of these acids now that we have some more information. So let's take these two, chlorite and chlorate. How would you name chlorite if it enters into a union with a hydrogen and makes an acid? Well, it would be the chlorous acid. Yeah. And what about chlorate? Chloric acid. Yeah. What about these two hooligans, sulfate and sulfite? Well, we would make sulfuric acid and sulfurous acid. What about phosphate? What's going to happen here? It's going to get that ic ending, phosphoric acid. What about acetate? Acetic acid and carbonate? Carbonic acid. There you go. See how much you know? I think it's time for a flow chart. So how do we go about naming these acids? Well, first of all, you have to determine whether it's a binary or an oxyacid. If it's binary, it's pretty straightforward. You give it the hydro beginning, the acid end, and you take the nonmetal and add ic to it, and you put it all together. If it's an oxyacid, it's a little bit more elaborate. You have to look at your oxyanion and determine whether it has the ite ending or the ate ending. If it's got that ite ending, you would change it to an us and add acid. If it's got that ate ending, you would change the name of your oxyanion to that ic ending and name it acid. So there's your flow chart right there. Oh yeah, why not another flow chart? I'll hang out here for a second, let you look at it. You could always take stop the video, take a picture of the screen and save it. So on any of these, that might be what I would do. The flow charts for solubility would be one that I would do this with, and probably the slide previous to this one would be ones that I would use for reference. Hey, let's try our hands at even more. So let's look at what we have in the first one. I guess the first thing that I would ask ourselves, are we dealing with an oxyacid or are we dealing with a binary? Hopefully you said binary, because all we have are hydrogen and sulfur in there. And to name that, we would have to put a hydro and an acid and an ic somewhere, so we would end up with hydrosulfuric acid. What about number 2? Hopefully you said you're dealing with an oxyacid. And if you notice, we don't include hydro here. We're just going to look at what our oxyanion is and name that accordingly. So if we looked it up on a chart, we would see that we're dealing with an 8, chlorate, and this would be chloric acid. What about this crazy thing, number 3? Well, we're pretty sure we're dealing with an acid because we got the H in front. If you go to a polyatomic ion chart, you would see that the name of this oxyanion is acetate. And 8s get that ic ending, so this would be acetic acid. So there you go. So let's try this. What is the difference between hydrochloric acid and chloric acid? Well, hydrochloric acid is going to be your binary acid because all it is hydrogen and chlorine. And your chloric is probably going to be made of an oxyanion, which it is, which is HClO3. And it's going to be the version that has the 8 oxyanion. So your hydrochloric acid is binary, and your chloric is going to be made of an oxyacid with your 3 compounds as opposed to 2. So what happens when you mix an acid and a base together? Well, it can get pretty exciting depending upon what it is. But the thing that ultimately happens is that you have what you call a neutralization reaction. And in essence, what happens with these is that the acid is going to react with the base, and the two are going to neutralize each other, and what they're ultimately going to produce is water and some spectator ions. Yeah, you would thought of it had been like a big explosion, but it's not really. I mean, initially it might be because there's some energy that gets released, but typically no, it's going to be a quiet neutralization reaction. In acid-base reactions, as in precipitation reactions, the reactions are going to occur when we have our acid and our base in their aqueous form. So we're looking at ions suspended in solution with these reactions. So like I said on the previous slide, when an acid and a base come together and create a reaction, it's called a neutralization reaction, because what ultimately happens is that you're going to create a spectator ion, which we call a salt. In this case, it's going to be calcium nitrate, and we're going to create water. So let's take a look at how that happens. So here we have our 2 substances, and we put our nitric acid into water, and it's going to release that hydrogen ion and leave behind a nitrate anion. And calcium and hydroxide are going to do the same thing. I'm intentionally only showing one hydroxide ion. And when they undergo a reaction, it's going to end up, we mix them together, and we're going to have all 4 species in our vat. So what ends up happening is that the calcium can maybe come over here and hang out with the nitrate, and the hydroxide can come over here and hang out with the hydrogen ion. And what we've done is we've created water, which is a liquid, and calcium nitrate. So that's how that works. So as long as a salt forms that is soluble in water, the net ionic equation for an acid-base reaction can simply be a hydrogen ion, hydroxide ion coming together to create water. A neutralization reaction is complete when the moles of acid equals the moles of base in solution, because pretty much they formed all the water that they can. And interestingly enough, that just because you add an acid and a base together doesn't mean that you're always going to end up with a pH that's neutral. Depending upon the strength of your acid and base, it can either be more alkaline or more acidic. But that comes in chemistry too, so we don't have to worry about that here. So up to this point, we've been talking about how substances liberate these hydrogen ions in water. Well, here's the deal with hydrogen ions. They are very, very reactive. And once they get liberated in water, they don't stay a hydrogen ion. What they do is they'll find a water molecule. And if you remember, a water molecule has a couple of non-bonding electron pairs. And that hydrogen ion will sit there and occupy the space held by one of those non-bonding electron pairs on the oxygen. And what it creates is something known as a hydronium ion with 3 hydrogens and an oxygen. So in this class, and possibly going forward, you will start to hear me use hydronium ions when we're talking about acids and bases. And I'll use them interchangeably with your proton or your hydrogen ion. Now, bases are going to dissociate in water to form hydroxide ions. And as I addressed earlier, your ammonia is going to do something funny and not release a hydroxide ion itself, but produce one by pulling a hydrogen ion off of a water molecule, leaving behind a hydroxide. So when you have an acid and a base coming together, your hydrogen ion is going to form water with the hydroxide ion, and what gets left behind is going to be that salt, also known as a spectator ion. And this equation, these equations pretty much follow the pattern that you see right here. So let's take a look at example 8.12. We want to write the equations for this acid-base reaction involving acetic acid and potassium hydroxide. So the first thing we want to start off doing is writing the molecular equation. So we're going to write our acetic acid and our potassium hydroxide. And our potassium is going to hook up with the acetate, and the hydrogen is going to hook up with the hydroxide. So we're going to end up with water and potassium acetate. So that is the first thing that we're going to do. Now the next thing that we're going to do is that net ionic equation. And that's going to be where we tease out everything and write it in its ion form. So we are going to write our acid, and we teased out the potassium and the hydroxide. Now they're leaving the acetic acid as a aqueous solution because it is a weak electrolyte, which means that with something like this, you're going to end up having some of the acid in solution, but you're also going to have some of the ions in solution because it's going to form an equilibrium. So that's why they do that. If you were doing this on my exam, I would like for you to tease out everything and not worry about weak or strong, any of that. And so that's what's happening on the left side. On the right side, we're making water, and we have our potassium ion, and we have our acetate ion, which is still aqueous. And if we look and see what we have happening here, we can see that our potassium has stayed an aqueous ion, so we can get rid of that. And at the end of this, what we end up having is our acid, our hydroxide ions, and water and acetic acid. Now this is the way your author of the book has asked you to do it. What I would ask you to do is the way I demonstrated just a few slides ago, where you tease out everything and you get rid of all the repeating terms. I'm sure that the way that this is being done is more correct, but for learning purposes where we are, I would be very happy if you guys would just tease out everything, get rid of the repeating terms, and show me what's actually being engaged as far as components that are making new substances. So let's see what we have happening here. What if we had hydrochloric acid and barium hydroxide? What would our products be? Well, our partners are going to do the do-si-do, which means our barium is going to hook up with the chloride and our hydrogen is going to hook up with the hydroxide. So we're going to end up making water and barium chloride. And we could write it in its ion form and balance everything out, and we would end up having this balanced equation. So what if we had sulfuric acid and lithium hydroxide? What would our products be? Again, our partners are going to do the do-si-do, and we're going to end up making water and lithium sulfate. And we can tease it all out, balance the equations, and it ends up looking like that. I think sometimes where students get a little tripped up is they don't know what's supposed to be on the other side of the transformation arrow. And it really is just as simple as the positive component of one compound is going to hook up with the negative component of the other compound and vice versa. And then you have to check with your solubility chart to figure out what you've created. Have you created a liquid? Have you created a precipitate? Or have you created something that's still staying aqueous? So that's how you start off with these sorts of equations. Now, if you've taken high school chemistry, you probably ended up doing a titration. And we were certainly going to do one in our lab. I hate to keep going there, but we were going to go there. So what is a titration? Well, a titration is when you drop a solution into another solution a little bit at a time, and you're waiting for a reaction to become visible. And so because a picture's worth 1,000 words, let's just go ahead and go to the picture. All right, so this is an example of an acid-base titration. So what's happening here is that you have a piece of equipment called a burette, and you have a little valve where you can turn on the flow or turn off the flow. And what's in your burette is a known quantity. You know the concentration of, in this case, your base. It's hydroxide. So we know what the concentration of our base is. What we're adding our base to is the stuff here in this flask, and this flask is going to contain an acid. And what we're trying to do is this acid-base reaction. Now, how do we know that our acid and our base have neutralized each other? Well, also in the flask with our acid is a color indicator. And what's special about this color indicator is that when our solution reaches a point where our hydroxide ions equal our hydrogen ions, the solution will turn pink. And that's how we know that we are there. And once our solution turns pink, we've reached what's called the equivalence point. The equivalence point means that we have equivalent amounts of hydroxide ions and hydrogen ions. So as this slide says, in an acid-base titration, because both of our solutions are going to be colorless, you need some way to have a visual indicator that something has happened. That's the indicator. The indicator tells us when we've reached the end point or the equivalence point of the reaction, because that indicator is going to change colors. The indicator selected demonstrates an endpoint, and it does so when the number of moles of hydrogen ions equals the number of moles of the hydroxide ions, and that happens at that equivalence point. So these are really good pictures because this is what happens. So you're adding your base, you're adding base, you're adding base, and then at some point you're going to add base and you're going to start to see this pink. But the pink will disappear because we haven't really reached the point where we have as many hydroxide ions as we have hydrogen ions. So there's still hydrogen ions in our flask that could take on more of the base. But in this little region right here where the base entered, there is an equivalence point that's been reached. It just hasn't been reached throughout the entire sample. And when you do reach the entire sample, the thing will stop going pink and then turning back to clear, and then it will stay all pink. And you can get variations of pink, and you want it to be about this color pink. So it's actually a nice experiment to do. I wish we could have done it. The indicator that's being used in this example, which would have been the one we would have used in our lab, is phenolphthalein. I'm mispronouncing it horribly. Phenolphthalein. There we go. Phenolphthalein. So yeah, it's kind of fun to play with that. So, and then we do a bunch of calculations around it. That's the downside. But the pink is really pretty. Okay, we've talked a little bit about gas evolution reactions when we were looking at combustion reactions. And a gas evolution reaction is one where one of the products ends up being a gas. And typically what you're going to see in your test tube or your vat is some form of bubbling. And you guys have had that experience where you've added a couple of substances together and you ended up getting the fizz or some bubbling. That was actually a gas evolution reaction taking place. Now, in both acid and base and gas evolution reactions, the reactions occur when an anion from one reactant combines with the cation of the other. So basically, our species are doing the do-si-do and switching partners. So no surprise there. Now, when we've spoken about most of the reactions up to this point, we've talked about having a couple of reagents or a couple of reactants that we mix together and getting a reaction pretty much on the spot. Gas evolution reactions can be a little bit funny because what can happen with gas evolution reactions is that you mix your two reactants together and you get a reaction, but then as things create a new product, that new product can undergo another reaction in and of itself. So you can actually end up having two reactions occur as a result of mixing a couple of reactants just one time. So for example, An example where we have gas being created directly is when we take potassium sulfide and sulfuric acid and we mix them together, we can create the spectator ion, potassium sulfate, but then we end up creating hydrogen sulfide gas, which is some nasty stuff. So you don't want to, you'll be doing that one in the hood. Yeah, you won't be doing that one at your desk. But that creates the gas in one step. The reaction where we were to take something like baking soda and mix it with hydrochloric acid, which is this next equation written out down here, that's initially going to form salt, sodium chloride, our spectator ion, and then it's going to create something known as carbonic acid. And carbonic acid, after a bit, will then start to break down and form water and carbon dioxide. So the first set of reactions created no gas, but the second set of reactions did. So this is what is meant by a gas evolution reaction. Might not directly create gas in the process. It might take a couple of steps. So I guess the question as a student would be, how are we going to know that? You're going to look at a chart. I wouldn't expect you to have this memorized or be able to intuit it. It's not necessarily that easy to intuit as a Chem 1 student. So yeah, you'd be looking at a chart for that. You'd be looking under the chart that says gas evolution reactions. Or you'd be looking at the sentence on the exam that says, in this gas evolution reaction, blah, blah, blah. So that's how that will enter your life in the future. So here's your chart for your gas evolution reactions. So if you have a sulfide as a reactant, you're not going to have any intermediate products. It's going to go straight to a gas that gets evolved. If you have carbonates and bicarbonates, you're going to initially create carbonic acid and then you'll create carbon dioxide. Sulfuric acid will initially, if you have sulfites or bisulfites, you'll initially create sulfuric acid and then ultimately create sulfur dioxide. So that you would look at the chart. That's what you would do. Just look at a chart. Okay, oxidation and reduction reactions. What does that mean? Well, oxidation and reduction reactions describe a scenario when you have the transfer of electrons in the process of a chemical reaction. And oxidation and reduction occur together. Basically what that means is that somebody's given up the electrons and somebody's finding them. And we've talked about this when we talked about ionic bonds. Let's see if my example's right here. Okay, so let's say that we had potassium and we had chlorine coming together to create potassium chloride. Well, this should not come as any surprise that calcium has 1 valence electron and chlorine has 7. And that in order for these two substances to come together, they're actually going to create an ionic bond, because potassium is going to form an ion with a positive 1 charge, and chlorine is going to form an ion with a negative 1 charge. Now, how do we get that positive 1 on our potassium? Well, it's going to lose that electron, and it's going to end up creating that positive 1 ion. And chlorine, well, chlorine found that electron, and as a result, it's going to create an ion with a negative 1 charge, because remember, electrons carry with them a negative 1 charge. So here we have our potassium with a positive 1 charge, indicating that it has lost an electron, and there's our chlorine with a negative 1 charge because it has found that electron. And that when we put these two together, that's how we end up creating the ionic bond between potassium and chlorine. So redox reactions help us track this. But instead of drawing out the Lewis dot, we actually do it through a numbering system whereby we assign something known as oxidation numbers. So again, to reiterate, oxidation and reduction reactions, redox reactions as they're also known, are reactions where electrons are transferred from one atom to another. Atoms that lose the electrons are being oxidized. So in our example here with potassium, potassium would be the one that is being oxidized. And the atom that finds that electron or gains the electrons are the ones that are being reduced. And my example here, we have chlorine. Chlorine was the one that was reduced. So that's the language behind all of this. And let's put it to work. Just like that. So how do we set about quantifying a redox reaction? How do we get some data so we can do some analysis and figure out what the heck is going on with this thing? Well, what you're going to do is you're going to assign what's known as an oxidation number to your redox reaction. And it's going to, each element or polyatomic ion is going to end up getting an oxidation number. So let's bring up an equation and see what I'm talking about. All right, so here we have a molecular equation, and what's happening here is that we've got a solid zinc and an aqueous solution of copper sulfate. Going to mix those together, and what's going to happen is zinc sulfate is going to form. It's actually going to ionize, and then we're going to end up having our copper drop out of solution and form a solid. Now, in order to assign the oxidation numbers, I'm going to write this as an ionic equation. So what I've done here is I've left zinc solid as it is, but I've taken the copper out of the copper sulfate. And so I have copper, and then I have the sulfate ion. And I'm going to leave the sulfate ion as a polyatomic ion. It's easier to work with this way. And then on the other side of the arrow, we have zinc as an ion and sulfate as an ion, and then copper as a solid. Now I'm going to assign the numbers. I'm going to assign the numbers without telling you how I'm coming up with these numbers first. But in a minute, we're going to look at how to come up with these numbers. And then we're going to do plenty of exercise around coming up with these numbers. All right, so zinc as a solid is going to get an oxidation number of 0. Copper is going to get an oxidation number of +2. Sulfite is going to get an oxidation number of -2. Now these positives and these negatives are basically telling us about the movement of electrons, or the state of affairs with their electrons. And the inclination is to think of these as being the same as the charge, but it's not really. The charge is basically telling us about the state of affairs with our electrons, and the resulting charge, oxidation numbers, tell us about the state of affairs of the electrons. So and the accounting system that's built around it. I know it sounds crazy. It looks the same, and at this point in the lecture, we could probably say it looks the same and we're going to go with it. Don't tell anybody at IUPAC, they'll come and get me. All right, so what's happening on the right side of the transformation arrow? Well, we have zinc, and it's going to have an oxidation number of +2. Our sulfate is still going to have a -2, and our copper solid is going to have an oxidation number of 0. All right, let's take a look at what happened to zinc. So on the left side of the transformation arrow, zinc had a oxidation number of 0, and on the right side of the transformation arrow, that went to a +2. So what happened to zinc is that it gave up a couple of electrons to sulfate, essentially, and it became an ion of itself. So when you lose ions, you undergo oxidation. All right, let's take a look at copper. What happened to copper? Well, copper went from a +2 to 0. So in this case, what happened to copper is copper found a couple of electrons and returned to its ground state where it doesn't have any charge. And because it had a reduction in its oxidation number, we would say it underwent a reduction. So because we had an increase in the oxidation number for zinc, it underwent oxidation. And because we had a decrease in oxidation number for copper, it underwent what's called a reduction. Now the language in the lecture in the book gets a little funky. I'm going to use it right here. An agent that undergoes a reduction is an oxidizing agent. The agent that undergoes an oxidation is a reducing agent. So it's like if you do the thing, then you're the agent of the opposite. So yeah, if you do the thing, oxidize, then you are an agent of the opposite, which means you're a reduction agent. Okay, I hope that makes sense. So how did I come up with those numbers? Well, I'm sure there's a very wordy explanation in the book. I've come up with a chart that I think is pretty simple to utilize, and here it is. So first thing, if you have an element by itself, the oxidation number is 0. If you have an element by itself, it's typically in its ground state. So it's not going to be at a loss for electrons, nor has it gained any. So its oxidation number, it's going to be 0. If you are a group 1A element in a compound, it's going to have a positive 1 oxidation number always. If you're a group 2A, you will have an oxidation number of positive 2 when you're in a compound. If you are group 7A, usually you're going to be a negative 1 for an oxidation number, unless you're with oxygen, in which case you will be a positive 1. All right, so that's part of it. There's more. There's always more. And here it goes. If you are a monatomic ion, such as calcium or magnesium, then your oxidation number is going to be the same value as your charge. So where you have a charge of 2 plus for calcium, the oxidation number is going to be plus 2. Okay. If you're hydrogen, it really depends on who you're coupled up with. If you're coupled up with a non-metal, then your oxidation number is going to be a positive 1. If you're coupled up with a metal, then your oxidation number is going to be negative 1. If you're oxygen, your oxidation number is usually going to be negative 2, unless you're in with hydrogen peroxide, in which case your oxidation number will end up being a negative 1. But that would be a special case. And if you are fluorine, your oxidation number is always a negative 1. Okay. And there's a couple more. The sum of oxidation numbers for any neutral compound has to equal 0. So if you have 2 elements in your compound, then the addition of the sum of their oxidation numbers has to equal 0. The sum of oxidation numbers for polyatomic ions are going to be equal to the ion charge. These are the rules. I like writing them this way because it's real easy to see. Not very wordy. It's just right there. So let's try our hands at it. So let's bring up one. We have carbon. What rule are we going to use to assign an oxidation number for carbon? Well, carbon is an element by itself, which means its oxidation number is going to be 0. All right, let's do another. Oh, what do we have here? We have aluminum with a floaty positive 3. Well, that would mean aluminum is a monatomic ion. And what's the rule for monatomic ions? It gets the ion charge, which means that the oxidation number for the ion of aluminum is a plus 3. Oh, what about aluminum in the ground state? Well, in this case, it's not a monatomic ion. In this case, it is an element by itself, and its oxidation number would be 0. What if we had magnesium by itself? Magnesium is a group 2A, but it's an element by itself, so it ends up getting an oxidation number of 0. What if magnesium was in a compound like magnesium oxide? Well, now we have the rule that says the sum of oxidation numbers for a neutral compound has to be equal to 0, which means that magnesium is going to be doing something and oxygen is going to be doing something, and they're both going to have some sort of an oxidation number. Well, the rule for magnesium says, because it's group 2A, that it's always going to be a positive 2. That is when it's in a compound or in its ion state. And oxygen is always going to be negative 2 unless it's in hydrogen peroxide, which is not. And we can see that the plus 2 of magnesium and the negative 2 of oxygen is going to be equal to 0, and that fits the rule that says the sum of the oxidation numbers for a neutral compound equals 0. So that's how that works. What if we had something like hydrogen chloride? Well, we'd have to look at the rule for hydrogen for starters. So hydrogen is going to be a positive one with non-metals and a negative one with metals. What is chlorine? Chlorine is a non-metal, so hydrogen is going to be a positive one, and chlorine is a group 7A, and it's with hydrogen, not oxygen, so it's going to be a negative one, and the positive one of hydrogen and the negative one of chlorine are going to come together and give us a 0 for the overall oxidation number because it's a neutral compound. What if we had something like water? Well, hydrogen is with a nonmetal, which means that it's going to have a positive 1 charge, but we have 2 of them. We have 2 of them, and we have to take into account the fact that we have 2 of them. So we would take the positive one of just a single hydrogen, and we would multiply it by 2. So the effect of hydrogen's oxidation numbers is going to be a positive 2. Which is great because it offsets the oxidation number for oxygen, which is a negative 2, and we end up with a neutral compound with no charge. What if we had something like this, NO3? There's a rule for this, and it's called the polyatomic ion rule. And it says the sum of oxidation numbers for polyatomic ions is equal to the charge of the ion, and in this case, it would be -1. So this is how you apply those rules. And that is how I apply the rules for assigning the numbers in the equation that we first looked at. So let's take a look at this equation where we have lead and sulfuric acid coming together to make lead sulfate and hydrogen gas. Now that we know what the rules are, I'm not going to bother to tease out the ions. We're just going to go ahead and start filling in the oxidation numbers. So for lead, ground state lead, an element by itself, oxidation number is going to be 0. Let's look at hydrogen. So we have some rules for hydrogen. The rules say that if we are with nonmetals, we're going to have a positive 1 charge. Let's see, sulfur and oxygen, they are both nonmetals. So our hydrogen is going to be a positive 1. But how many hydrogens do we have? We have 2. So the overall oxidation value of our hydrogen is going to be positive 2. That's going to be important because when we look at what our sulfate ion is, it comes in with a -2. So we have a positive 2 and a -2. The oxidation numbers go to 0, which means that this is a neutral compound, which it is. I don't see any charges floating around it. So yeah, we're good with that. All right, let's take a look at lead. Well, lead is going to have to offset the -2 of our sulfate, which means that our lead is going to come in as a positive 2. See how I backed that in? I didn't know what lead was because lead could be 2 things. Lead could be a positive 2 or lead could be a positive 4 because lead can form 2 different types of ions. And not knowing which one it was, I had to look to something that I did know about in my formula, and I did know about sulfate. So that's how I did that. All right, what about our hydrogen gas? Well, this is technically a neutral compound, but the way we would get a neutral compound is if one of those hydrogens had a negative charge, which it's not going to. So when you have a molecule where you have 2 of the same element, like hydrogen or chlorine or nitrogen, the oxidation number on each one of those is going to be 0, and the overall effect is that you have a neutral compound, and the oxidation number will be 0. All right. So now that we've assigned oxidation numbers, can we determine who has been oxidized and who has been reduced? Of course we can. We can look and see what's happening. Who has changed? Well, the first thing we can see is that good old lead has undergone some sort of transformation. It went from a 0 to a positive 2. That means that it went through oxidation. It is the reducing agent. Now our sulfate stayed the same, but what happened to our hydrogen? Our hydrogen went from a positive 2, got my square wrong there, to a 0. Yep, and all my animations are wrong, but I'm going to leave it at this point because it's midnight and I'm tired. So yeah, we went from a +2 to a 0. So in this case, our hydrogen was reduced. It is the oxidizing agent. So that's what that tells us. This is what we're looking for. That's how we know who has been oxidized and who has been reduced. So why are we assigning these oxidation numbers? Well, the chemists do this. They are basically determining what's known as the oxidation state. And by determining oxidation state, it allows the chemist to determine the flow of electrons in the reaction. And as we've studied pretty much from the very beginning, it is the movement of those electrons that is driving bonds and all kinds of reactions. So understanding that flow is important. Now, this is basically a very elaborate accounting system that is helping us get some sort of an understanding, a concrete understanding about what these electrons are doing. So that's really what this is. It's just an elaborate accounting system, a contrived accounting system. So, and here's the slide that says, even though they look like them, oxidation states are not ion charges. Oxidation states are imaginary charges assigned based upon a set of rules, and ion charges are real. They're measurable charges. It shows what happens once the electrons show up or leave. So that's the difference. But you can actually use the ion charge to determine oxidation number, even though they're not the same thing. So there's that. As stated originally, oxidation and reduction must occur simultaneously. If somebody's being oxidized, somebody's being reduced. The reactant that reduces the element in a reactant is called the reducing agent. The reducing agent is undergoing oxidation. The reactant that oxidizes an element is known as the oxidizing agent, and the oxidizing agent is the element that is undergoing reduction. Hopefully that makes it clear. All right, we have this thing called activity series. What is that? Well, if you were to put different sorts of solutions together that had metals in them, you would find that certain metals react more vigorously than other metals. Certain metals are more likely to form a reaction than other metals. And this has to do with the nature of the metal and some trends that we see in the periodic table. And we call this activity series. So an activity series helps predict whether or not a reduction-oxidation reaction will happen spontaneously, that is, without any additional energy. So basically what we're saying is that if we had two metals together in a reaction, it's basically a race. Who's going to react first? Who is more likely to undergo a reaction? And the thing that a lot of students find confusing about these is that they get written in this very cryptic notation right here. This doesn't look like anything. And it doesn't look like anything happened because you have magnesium and copper on one side, and then you have magnesium and copper on the other side. But what this equation is trying to show you, this is not a balanced equation. This is not telling you about the other things that were in the solution. This is just looking at who gave up the electrons and who found them. So this is very, very cryptic. It's not balanced. It's just, show me the flow of electrons. And what we see here in this first example is that magnesium solid was combined with a copper ion. And what ended up happening is that we created copper solid, so we have a precipitate of copper, and we have magnesium now suspended in solution as an ion. So this is an example of isolating the redox reaction, just looking at the elements that are undergoing the reaction without regard to anything else that is, without regard of what these might even be attached to and what their influence is, what the influence of those species are. In the second reaction, we have copper sulfate and magnesium ion undergoing a reaction where they say something happened, but something is not going to happen. So let's see what happens. This would be an example of that right here. So even though we wrote it out, we can see that nothing really happened here. We got nothing. Now, why is that? Well, let's have a look at the chart. So this is a fabulous little chart that tells us about the activity of different metals, about how reactive they are. How likely are they to form an ion? Well, the most reactive, shouldn't come as a surprise, is lithium. Lithium is very, very excited about liberating that valence electron and taking the ionic state that is similar to helium. And in fact, it will do so more vigorously than any other metal in this chart. It'll do it faster than potassium, which is the next most reactive metal. And it will do so, potassium will react faster than calcium, which is the next one in the chart. And if we're looking at the chart, calcium will react faster than sodium, and sodium will react faster than magnesium, and so on and so forth. So what we end up happening is that the elements at the top of the chart are going to be far more reactive than the elements at the bottom of the chart. So if we were to say we had a reaction that was involving lithium and nickel, if we had lithium solid and nickel in its ionic state, would the likelihood of this reaction go forward? Would it be likely that our lithium would create an ion of itself and that nickel would end up becoming a precipitate? Well, we have to look at the activity series table and determine who's the driver here. Well, since lithium is higher in the chart, it is the most reactive. It will be the one that reacts the fastest. It will be the one that reacts first. So for lithium to go from its solid ground state to an ion, that's going to be a driving force. So yeah, this reaction would happen when you put lithium in with nickel. Actually, when you put lithium in with anything, if lithium is solid and ground state, it's going to seek to liberate its electrons and form the ions. What if the tables were reversed and instead of starting out with lithium in the ground state, we started out with lithium in the ion state and nickel in the ground state as a solid? Would this equation move forward? Well, in doing so, what would have to happen is lithium would have to undo being in its ionic state, which it loves oh so much, and go back to being a ground state element, which it doesn't really want to do. Lithium likes being an ion. It really likes that. So the likelihood that we can talk lithium into becoming a ground state element, that's pretty much a no-go. So this equation is not likely to happen, which is why what we saw a moment ago on the other slide, that when we looked at calcium and magnesium reacting, it would only go under certain circumstances. So lithium will react with nickel as long as lithium is going from ground state, solid, to an ion state. What if we had something like this, where we had lithium and nickel competing to bind up with oxygen? Who do you think would win this race? You think nickel would? I don't, because nickel's not that reactive. It's pretty far down here in the chart. But I would place my money on lithium. And in fact, what would end up happening is that we would form lithium oxide and nickel would just be kind of hanging around doing nothing, twiddling its little proverbial thumbs. And that, my friends, is the end of chapter 8. Hallelujah, brother. On to 9.